Hi, I'm Idot Sameret from Imperial College London, and I'm going to speak about the joint work with Rahul Santhanam from Oxford University. So what we've done is we've taken this classical idea of diagonalization and applied it in a new way in proof complexity. And I'm going to show you precisely what we've achieved, how we've done this in very, very brief and in light details. And I hope you enjoy this talk. Let us discuss first the context of this work. So the context is the attempt to prove these big lower bounds. And these are the fundamental hardness questions in complexity theory, namely unconditional or sometimes conditional size lower bounds on concrete computational models such as circuits, algebraic circuits, decision trees, and in this case, in our case, it will be proofs and propositional proofs, with the ideal goal, of course, to separate complexity classes like P versus NP and so forth. So this is the context of this work. And specifically, the overarching goal for us will be to try and use diagonalization, this old traditional technique from set theory that was used in computability and in proof theory and logic, and also to a certain extent in complexity theory, to use it in new ways in the area of proof complexity. And proof complexity is an area that studies proof systems, and it is quite surprising that actually diagonalization was not extensively used in this area, except these sources that I mention here, which is Friedman from 79 and later Pudlak from 86, who considered lower bounds for first order proofs for consistency statements, and also the more recent work of Krycek from 2004. But the work of Krycek was for propositional proofs, but it is a different work than what we do. So let me give you the basic concept that you need to know for this talk, and they are very few. And this is about propositional proof complexity. The only thing you need to know is the following. A propositional proof system, denoted R, for us will be a polytime relation, polytime computable relation, and it may also be probabilistic polytime computable relation, such that the following occurs. So F is a DNF tautology if and only if, when we consider F and input it into our relation R, then there exists a string pi considered as a proof that gives it the value true, the relation. And this occurs if and only if F is a tautology. So this, you can see, is a complete and sound proof system. And what is the proof complexity of F? It's simply the minimal length of this string pi. And the basic goal, or the major goal of proof complexity, is to show that there are hard instances for a given proof system, namely hard family of DNFs Fn that do not have proofs that are bounded by polynomial. Now let me discuss the main idea and go straight into what we have proposed and what we have investigated in our work. So what we've done is the following. We put forth this operator, lower bound operator, and investigated it in different settings. So the operator that we have investigated is the following. We call it a lower bound operator, and it simply is a map that from DNFs to DNFs. And we denote it by lower bound R. It is parameterized by the proof system R. So lower bound R is a mapping from DNFs to DNF that does the following. And this is how it is defined. If the F is some DNF, then lower bound R of F is simply a new DNF that expresses the following. It expresses the fact that X, a set of propositional variables, is not a size polynomial in F, R proof of F. And this is it's possible to encode this as a DNF. And these are variables. And because this is tautology, it means that there will indeed not exist a polynomial size, in this case, F to the power of C, size R proofs of F. So let me discuss and consider some questions about this operator in order to clarify it. So F is a hard tautological DNF. Let's assume this. Now think about this. It's not completely clear what happens when we iterate, when we apply the operator. So what we do is we are going to iterate this operator over F. Maybe one time, maybe two times, and further. So if we iterate it or apply it once, what we get is the following. Of course, this is an operator that says, this DNF says that there is no small size R proofs of F. So if this is hard, we know that this is indeed a tautology by definition or construction. But we don't know that it is hard. Maybe it is tautology, but actually there is a small proof or short proof in R of the fact that there is a lower bound for F in R. And the same happens when we iterate again, and this is how I write it. I write it lower bound R with a superscript 2. So if we iterate it twice, what we get is the following. It's a statement stating a lower bound on the statement that states a lower bound for the proof system R on the tautology F. So what happens here is that if indeed this is hard, similarly to the previous case, if this is hard, then this is a tautology. But we don't know if it is hard by itself. We know it is just tautology. And now, of course, we can continue this iteration n times, and n here is a parameter. And this means that we consider the lower bound for R of the lower bound for R and so forth with this constant seed F. And the question that we ask in general is, do we actually maintain hardness for all n this way if we start from a hard F? Now, let me stress that there are two different settings that we consider. The first one is the setting that I'm going to focus in this talk mostly, and this is the iterated lower bound formulas, which take the following form. So we start with this constant DNF, the constant seed, so to speak, and we use n from 1 to infinity. So we apply lower bound ad infinitum, and that's way we get a family of DNFs, an infinite family. And we can ask whether it is hard in the sense of whether R possesses short or polynomial size proofs of this family of DNFs. And the second setting is the following. Fn is actually an infinite hard family, maybe a distribution of DNFs, and we consider k as constant. So we iterate lower bound operator constant many times. It still is an infinite family, but not because k goes to infinity, but because Fn is parameterized by n, which goes to infinity. And let me discuss quickly our results. So to understand our result, you don't need much. We already know what is proof complexity, or what is the basic concept of propositional proofs and proof complexity. And you also might want to recall the following definitions, but they are not really essential here. It's the algebraic version of P and the algebraic version of NP. And algebraic version of P, denoted Vp for some fixed field, let's say the rationals, is simply the class of all polynomials of polynomial degree who are computed by polynomial size circuits, small algebraic circuits. And here is a depiction of an algebraic circuit. It's the same concept as Boolean circuits, only that we consider it over a field and the gates are not logical, but algebraic, plus and times, and at the output you compute some polynomial. So the algebraic version of P is Vp over some fixed field f, and it is more or less the class of efficiently computable polynomials. On the other hand, we have Vnp, which is slightly more complicated to define. And what we need to know is the following. You need to know that there is a conjecture that they are indeed separated, somewhat like the conjectured separation of P from NP. And here I put the definition and some examples. So example of a polynomial in algebraic P is determinant, while an example for Vnp is the permanent, which is complete for this class, and this if you want to see the precise definition. Now, another concept that is helpful here is the concept of an algebraic strong proof, and here we are going to use the IPS, ideal proof system, as defined by Groucho and Pitassi. And this you can consider again intuitively as an algebraic version of propositional logic with extension variables. I'm not going into details here, it's not essential for this talk. But you only need to know that it is a very strong propositional proof system and it is open whether there are hard instances for it. And let's discuss now the first result, which is theorem 1. So what we've shown is an equivalence between proof complexity lower bounds and algebraic circuit lower bounds in the following sense. Vp is separated from Vnp if and only if there are no short proofs in IPS of the following DNF family. And the following family is precisely a DNF, a family of formulas that states that there are lower bounds for IPS when it comes to prove that Vp is unequal to Vnp. And this is encoded as a DNF, and this by itself, this in brackets, by itself is a specific DNF that fed into this operator LB-IPS. So this is an infinite family of DNFs. And this shows this very interesting equivalence. Now let me be slightly more careful and explain something that might be confusing. This DNFs might not be even tautologies. In this case, this one direction is trivial. Of course, there are no short IPS proofs if it's not a tautology, because simply there are no proofs anyway. And this is this case. But we do not know if it is a tautology or not, and this is the regime we work in. We work in the regime and this is an established regime in proof complexity, where people consider a family of DNFs or families of formulas that we don't know if they are tautologies or not, but we still want to say something about the proof complexity hardness. Now, although we don't know they are tautologies, we can conjecture that they are, and this is based on the algebraic version of Rasborov conjecture. So Rasborov conjectured that it is hard to prove in propositional logical proof systems, strong ones, circuit lower bounds. So we can define the algebraic analog of Rasborov conjecture as the statement that there are no algebraic proofs, in this case IPS proofs, of algebraic circuit lower bounds, which is precisely saying that IPS doesn't have short proofs for the statement that Vp is unequal to Vnp. So notice the following. If we assume this algebraic analog of Rasborov conjecture, we get that this is a tautology, but as I mentioned before, the fact that this is a tautology doesn't mean that it is hard. And what we show is that under VP unequal to VNP, indeed, this is a tautology based on this conjecture, but it is also hard. Now, this contributes to establish direction in proof complexity, connecting circuit and proof complexity in the algebraic settings, specifically Groucho-Pitassi, and they showed the following. They showed part of one direction. They show that if we have a lower bound for IPS, then we have VP unequal to VNP, and we show the other direction. Also works by Force, Pilka, myself, and Vigderson, and Lee, myself, and Vigderson, and Alexeyev, Grigoriev, Hirsch, and myself have discussed and investigated different kinds of connections between circuit and proof complexity in the algebraic settings. Other connections are, and a contribution for this theorem is for meta-mathematics of proof complexity lower bounds. We say something about the ability of IPS or strong algebraic proofs to reason about themselves. Namely, we show conditionally that IPS cannot prove its own lower bounds. And this relates to recent results by Pich and Santanam, and also an interesting survey by Podlak from last year. Now let me provide a gist of the proof. I'm going to give a very, very quick run of this of one direction, and this is the direction from VP unequal to VNP, implying this is hard for IPS. And what we show is the following. So let's take this notation, which means simply that IPS has small, namely polynomial size proofs of this statement. Now, polynomial here is basically a fixed polynomial that we fixed. And we consider the following. Let's assume that there is a proof of this statement, that there is a lower bound for IPS for this statement. Now, notice that I've used this color for this statement, and this color and size will mean that it is of certain dimension. When I'm talking about this color and this size, it is a different, of course, statement. This is just an encoding of this statement for a specific dimension. Now, if we assume this occurs, this holds, then I'm going to show that from this, I can actually derive with efficiently in IPS a statement that VP is unequal to VNP. But this is a different color, meaning, and a different size, meaning this is of a different dimension, just to be clear. So if I have a statement saying that there is a lower bound for IPS for this DNF, then I'm going to derive this. And how can I do this? So basically, we have to formalize Groucho-Pitassi work. And as I've mentioned before, Groucho-Pitassi showed indeed that if we have a lower bound for IPS, then actually we can conclude VP is unequal to VNP, and we can what we show is we can formalize it in some quite complicated way in IPS itself. And that's how we get this. But this doesn't conclude our theorem yet. What we show is that we need now to apply another iteration of this lower bound operator in order to conclude our theorem of this direction. And this is what we show. So if this this pink VP unequal to VNP has short IPS proofs, it means basically that when I apply the operator on this statement, the pink one, then it is not a tautology because we've just showed that it has a small proof. And this means that it doesn't have one. So basically, because it is not a tautology, this is not provable simply because IPS is sound. And this we concluded based on our assumption that this has a small proof. So either this doesn't have a small proof or this doesn't have any proof. And this is how we conclude this direction. Now, we also show the following. And this is new in the sense that it does not appear in the camera-ready version of the STOC, but I still think it is interesting and it is important to provide it because we got it after the STOC version. And this shows the following. Assuming the algebraic analog of Rasborov conjecture, Vp unequal to Vnp in fact is equivalent to the iterated lower bound formulas. And this means the following: lower bound n IPS, and inside this constant seed f. Namely, these are hard for IPS if and only if Vp is unequal to Vnp. And this is based on this assumption. Now, we've discussed the algebraic settings, but you might be very interested actually in the propositional setting and what our operator and iteration of operator show about lower bounds in this setting. And we ask the following: is it really, to iterate this lower bound operator, does it constitute a good hard candidate for general propositional proof systems? And here is what we can say. First, we put forth this hypothesis. It's not precisely a conjecture because there might be some cases where it's not true or we are not convinced that it is true. So the hypothesis is the following: iterated lower bound formulas like this are hard for every reasonably strong propositional proof system that is not polynomially bounded. So we think that this may be strong for every propositional proofs, and we show some initial result. So first, by theorem 2 that I've just described, it actually holds for IPS conditionally on the algebraic version of Rasborov conjecture. But actually, if you consider also resolution, this popular refutation system, it holds for this. And this hypothesis holds for resolution because of Atzerius and Muller result and Garlick result from 2020 and 2019, respectively. So we have some initial justification for this hypothesis. Now, something that is quite interesting is the following dichotomy theorem. So this dichotomy theorem shows the following. This is theorem 4. For reasonably strong R proof systems, and here reasonably strong means they prove reflection principle, the iterated lower bound formulas are either of the following form. Either they are all tautologies and hard, and this is very good for us because that's our goal, or something strange happens. They alternate from some point, namely from some n, they alternate between having short proofs and not being even a tautology. And they actually alternate step by step. So one has no short proofs, and the next one is in tautology, and the next one has no short proofs, and so forth. Now, this is a very nice logical exercise, and I suggest you to read this proof that shows, that actually explains why this happens. Now let me discuss the final result, which is theorem 5 for this talk, which deals with the constant number iterated for the lower bound operator. And this shows the following. Let Fn be a family of random truth table tautologies, and they are tautologies with high probability, and this truth table, random truth table formulas claim the following. They are formulas or DNF formulas stating that a function given by a truth table does not have a small or polynomial size Boolean circuit. And we know that this is true with high probability. So these are tautologies with high probability, and let's assume the Rudich conjecture, which is written here. There are no short propositional proofs for random truth table tautologies. So what we show is the following. Based on this conjecture, for every constant k, if we consider this, but this is constant, this is infinite, is hard on average for some strong propositional proof system R. This one, if you look up the paper, you see that this one is written explicitly. It is a certain proof system that extended Frege. But I don't want to get into the details. And this is the theorem 5. So basically, that's it. I hope you enjoyed this talk. Thank you.